Here this is system, this is surrounding, and this is the boundary. This can be permeable or it can be impermeable. This is based on the kinds of boundaries. Thermo means heat, dynamics means flow. The overall content or overall study of flow of heat will be called as thermodynamics. For 1 mole of ideal gas, then the value of pressure automatically gets fixed, that is P equal to RT by V. Hello everyone, this is Harshita Bhavasar from Vidhyaashram School of Excellence. Today we are starting up a new lesson, that is thermodynamics. So first we'll see the exam corner from this board. The number of hours given for this chapter is 20 and the overall marks allotted for this unit is 11 marks. So what are the contents we are discussing today is introduction to thermodynamics, limitations of thermodynamics, terminologies in thermodynamics, reversible and irreversible processes. The overall introduction part of thermodynamics, what are the terms will be used in this dynamics flow, and the types of process, that is reversible and irreversible process, and after that we'll be seeing the limitations of the thermodynamics also. So first we have to understand what is thermodynamics. Thermo means heat, dynamics means flow. The overall content or overall study of flow of heat will be called as thermodynamics. By using the chemical energy present in the molecule, we can see the mechanical work, we can see the physical work, or we can see the overall work or internal energy. Any kind of work can be done by using the chemical energy which is present in the molecule. So the dynamics, the flow of heat is very much important. The study of flow of heat or the study of thermodynamic transformations can be seen in this chapter. Chemical energy stored by molecules can be released as heat during chemical reactions when a fuel like methane, cooking gas or coal burns in air. Whatever the chemical energy will be released or will be stored in the molecules can be released as heat during the chemical reactions when a fuel like methane, coal or cooking gas is in air is present. The chemical energy may also be used to mechanical work when fuel burns in an engine or to provide electrical energy through a galvanic cell like a dry cell. Whatever the chemical energy which is stored by the molecules can be used as heat in the form of mechanical work also, which will be provided to the electrical energy also for the usage of galvanic or dry cell. Thus, various forms of energy are interrelated and under certain conditions, these may be transferred from one form to another form. We know that energy cannot be created nor be destroyed, but it can be transformed into one form to another form. We know here heat is a part of chemical energy, so it can be transformed into one form to another form, like mechanical work, like chemical work, like this. The study of these energy transformations forms the subject matter of thermodynamics. It is a study of transformation of energy. Heat is nothing but energy. So overall in this chapter we will study the transformations of energy. It is widely applied in the fields of physics, chemistry, biology and engineering also. Where we will use this thermodynamics part majorly is physics, because this chapter will come under physical chemistry, and chemistry because to study the macroscopic subject like matter and energy, and biology and also in engineering theories. What is the usage of the study of thermodynamics? It helps us to predict the feasibility of a reaction. How much the reaction is feasible or non-feasible, to predict that one, it is useful. Determine the extent to which a reaction proceeds. Select a suitable conditions for the reaction. By seeing the flow of heat or by seeing the energy, the transformation of energy, we can predict the condition which is suitable for the reaction. Calculate the efficiency of engine. Find out the maximum work can be obtained from a system. How much work has been done by the system also can be calculated. Thermodynamics is organized around three basic laws that govern transformation of energy in macroscopic system. There are major three laws, that is first law, second law and the Zeroth Law of Thermodynamics, which govern the macroscopic study and the transformation of energy. As it deals with only matter in bulk and measurable properties like pressure, volume, irrespective of its atomic nature, thermodynamics has become a subject of immense reliability and greater applicability. The major thermodynamic variables are pressure, volume and temperature. After reading this, there is a greater applicability and reliability of this subject. What are the limitations? It deals with macroscopic systems and does not provide an insight into the atomic molecular approach. As we have seen the introduction part of thermodynamics, it studies about or it gives the information about macroscopic subject but not about the inside of the molecule and the atomic approach. It does not provide information about the rate of a reaction. Rate means nothing but time or speed of a reaction. It will not give the information about the rate of a reaction. It does not offer details about mechanism of the reaction in thermodynamics. Means reaction means we have to understand that mechanism wise we will understand the step by step reaction, but the thermodynamics will not give any details of the path of a reaction. How the reaction has been proceeded, we doesn't know. Only the initial and the final product can be seen. These are the limitations of thermodynamics. Next one, terminologies in thermodynamics. Since it is a little bit new chapter about the heat, we have to understand so many terms regarding this chapter. First one, system. It is a specific part of the universe under study. It is isolated from rest of the universe by a definite boundary. System in a thermodynamic sense is always macroscopic. Means if you take a beaker, into that water is present, means this is a system. Surrounding to this system is this surrounding. This is system. It is a specific part of the universe. This is a specific part of the universe. This is system. It is isolated from rest of the universe. This is isolated from the rest of the universe having definite boundary. This is nothing but boundary. Hot water in a beaker. That's what here. If you take the hot water or cold water, it will be in a given system. System in thermodynamics is always a macroscopic. Yes, we are studying about the macroscopic levels. So, system is also a macroscopic level. It is under macroscopic level. Next, surroundings. The rest of the universe besides the system forms surrounding. This is system means there beside or rest of the universe will be considered as surrounding. A boundary is a real or an imaginary wall between system and surrounding. If this is a system, this is a surrounding, means this is a boundary. It can be real or imaginary line between the system and surrounding. Some of the types of boundaries are a rigid wall whose position and shapes are fixed. If it is impermeable, it does not permit the passage of matter. If this is an impermeable boundary, means this matter cannot come here or this matter cannot move into that system. Means the exchange of matter cannot be taken place. An adiabatic boundary which will not permit the passage of matter of energy. An adiabatic boundary means it will not permit the passage of matter of energy. A thermoflask means if you keep the hot water in the thermoflask for 9 am till evening or till night, it will be hot only. Means the exchange of energy cannot be taken place in that thermoflask. A diathermic wall which will not permit the passage of matter but allow the passage of energy. In the diathermic, which will not permit the passage of matter but the energy will be passed. See here, this is system, this is surrounding and this is the boundary. This can be permeable or it can be impermeable. This is based on the kinds of boundaries. Next one, the types of system. There are three kinds of system, that is open system, closed system and isolated system. An open system is one which can exchange both the matter and heat energy with the surroundings. Here the boundary is not sealed and not insulated either. So example, water in an open beaker. For this, if you open the beaker, If it is present, the water is present in the open beaker, here exchange of gas and exchange of matter and heat will be exchanged between surrounding and system. A closed system is one which can exchange heat energy with the surroundings but not matter. If it is closed, this is heat is given, correct? Here heat exchange will take place but not matter. Example, ice kept in a closed beaker. An isolated system is one which can exchange neither matter nor heat energy with the surroundings. An isolated system will not have any interaction with its surrounding. Same thing, no interaction with surrounding means no exchange of matter or heat in the isolated system. For this good example is thermoflask. Neither heat will be exchanged nor matter will be exchanged. See here, this is isolated system. Here exchange of matter, here closed system and here open system. Neither matter can be exchanged or energy can be exchanged. Here closed system, energy can be exchanged, matter does not, but here matter and energy both can be exchanged with the surrounding. Next, thermodynamic variables. Mostly the major thermodynamic variables are pressure, volume and temperature. Properties such as pressure, volume and temperature while help us to study the behavior of thermodynamic system are called thermodynamic variables. To study the overall thermodynamic reactions or any kind of the behavior, you have to know the properties of pressure, volume and temperature. So, we will be called it as thermodynamic variable. Next, state functions. The state of a thermodynamic system is described by the specific value of certain parameters called state functions or state variables. A particular thermodynamic system by a specific value called as state function. State functions depend on the initial and the final states of the system and are independent of the path taken by the system. Means it is dependent on the initial and the final step of the reaction, but it does not depend on the path which has been the reaction has been moved. It doesn't depend on the path or it doesn't depend on the mechanism route. Just it needs the initial and the final product. If we assign values of a few of these state functions, the others get automatically fixed. For instance, if we fix the value of the volume as V and the temperature as T for 1 mole of ideal gas, then the value of pressure automatically gets fixed, that is P equal to RT by V. The state functions are path independent. Yes, this is analogous to climbing a mountain. The vertical height we climb from one point to a mountain to a certain other point on it will be the same irrespective of the path taken. If it doesn't consider the path taken, the one point started from the mountain climbing and the other point which we have reached is one and the same. Let us consider a change of state in an ideal gas when the pressure of the gas changes from P initial, that is 1 atmospheric, to P final 5 atmospheric pressure. Volume and temperature of the gas also change. The change in pressure P final minus P initial, that is 5 minus 1, 4 atmospheric pressure will be given. The change in a state function depends only on initial and the final states of the gas, not on the method by which it was attained. Same thing we are telling by giving so many examples. State function means it is the independent of path taken. It just considered the initial and the final results of the reaction. Next, path functions. Those variables which depend on the path taken by the system to attain a particular state called path functions. Path function means itself only shows it depends on the path to reach a particular state. Energy transferred as heat and work done are path functions since the amount of work done or lost depends not on the initial and final states of the system, but on how that final state has been reached. If energy is transferred from one beaker to or one another substance means there is work has been done and the energy in the form of heat has been transferred, that is a path. So it has been depend on the path and part with respect to heat and work done. It can be done or lost, but how that final state has been reached, it will be dependent on the path function. Path functions are generally represented by small letters. See here, Q and W will be represented by small letters. Next, extensive and intensive properties. An extensive property is a property that depends upon the amount of substance present in the sample. An extensive property means how much of amount present in the substance will be considered as extensive property. An intensive property is a property that is independent of the amount of substance present in the sample. Extensive means it will depend on the amount of substance, but intensive it will not depend on the amount of substance. For instance, let us combine two systems, that is mass 1 and mass M2 at temperatures as T1 and T2 respectively. The mass of the combined system will be M1 and M2, but the temperature of the system will not be simple arithmetic summation. The temperature will be between T1 and T2, hence mass is an extensive while temperature is an intensive property. Because mass means the amount of substance present in the certain given object will be considered as a extensive, but temperature we cannot see or we cannot observe suddenly, so it will be considered as intensive temperature. The examples of extensive properties are mass, work, internal energy, entropy, enthalpy, free energy, volume, number of moles, heat capacity, which can be measured or which can be seen in terms of calculative things. It can be concluded as or considered as extensive properties. But the intensive property, temperature, pressure, density, viscosity, specific heat, boiling point, refractive index, molar volume will be considered as intensive property, which is not dependent on the how much amount is present. If you see the boiling point or if you are seeing the melting point, how much of amount can be to get the melt or to get into the liquid state, always the melting point will be the same, whether it is minute or it is the major kind of amount. See, this is the examples with the pictures. This is temperature, this is boiling point, concentration, luster, and here extensive weight, length, volume, entropy, which can be calculated very easily. Next, Zeroth Law of Thermodynamics. Zeroth Law came into being after the three laws of thermodynamics. It is stated as if two systems in that equilibrium with a third system, then all the three systems are in a equilibrium with one another. Yes. If A, B and C, if A is having equilibrium with B, then it will be having equilibrium with C, then automatically A will be having equilibrium with C. Then all the three parameters will be having the same equilibrium. That states the Zeroth Law of Thermodynamics. The thermodynamic process. The transition of thermodynamic system from one state, that is initial to final, is called thermodynamic process. Based on the conditions of change, they can be classified into different types. See, this is a Zeroth Law of Thermodynamics, a flow chart or a picture. Next one, the number of processes in the thermodynamic, that is isothermal, adiabatic, isobaric and isochoric process. In the isothermal process, it is a process in which the temperature of the system remains constant. Isothermal means constant temperature will be present throughout the system. Heat evolved by the system is immediately given out to the surroundings. Whatever the system evolved the heat, it will be given out to the surroundings immediately. Thus, maintaining a constant temperature of the system will be written as del T equal to 0. These processes are carried out in the thermostat. Next, adiabatic process. In an adiabatic process, no heat enters or leaves the system because in this system, the system and the surroundings are separated by a insulating walls. Here, heat will be evolved by the system and it will be given out to the surrounding. No insulated walls will be present, only temperature will be constant. But here, between the surrounding and the system, insulated walls will be present. No heat will be enters, no heat will be leaves from the system to the surrounding. Therefore, no heat is exchanged between the system and the surrounding during the entire process. Therefore, temperature will change. These processes are carried out in an insulated vessel. For adiabatic process, Q equal to 0 means heat equal to 0. Heat will be constant. Next, isochoric process. Volume of a system remains constant during the process. The change in a closed contained volume isochoric is equal to del V equal to 0. In the overall process, volume will be always constant. In the isobaric process, Pressure of a system remains constant during the thermodynamic process. Expansion of gas against atmospheric pressures is called isobaric, that is del P equal to 0. Then what is cyclic process? A process which brings the system back to its initial state after going throughout a series of changes is called a cyclic process. If it has been started from A, it moves to B, then C, then again it will reach to A. It has been started from A. After series of experiments or reactions or changes has been seen, it will reach or it will back to the original or initial state, will be called it as cyclic process, which will be called as del U equal to 0 and del H equal to 0, that is internal energy and enthalpy will become 0 here. Next, reversible and irreversible processes. In ordinary sense, as a reversible process means a process that can go both ways, that is a process that makes place in the forward as well as backward direction. But in a thermodynamic sense, reversible change means change that can take place in a system and its surroundings so that there is no observable change in the inverse. In normally reversible process means reaction can move forward or reaction can move backward. But in the thermodynamic sense, the change that takes place in a system and the surroundings, there is no observable change. In a thermodynamically reversible process, the change during the process occurs so slowly that the system and the surroundings always in equilibrium. In the thermodynamical reversible process, the reaction will move very slowly, that is finite similarly. And the direction of a process can be reversed by changing the driving force by infinitesimally small value. Reversible process is only an idealization but a useful one. In an irreversible process, the system after undergoing a change will not have the tendency to return the initial state. In the irreversible process, whatever the series has been taken place, it will never back to its initial state. There are so many differences between reversible and irreversible process. First, we will see the reversible. Process is carried out infinitesimally slowly in a infinite number of stages. But here, process is carried out rapidly in a single step, which is irreversible. At any state, equilibrium cannot be disturbed, but here, after the reaction only equilibrium can be exist in a stable manner. It is only an ideal, means hypothetical. It is only imaginary, cannot be achieved in actual process. Yes, most of the chemical reactions cannot be reversed as it has only the hypothetical region. It's a practicable process. It actually occurs in nature. Yes, most of the reaction after doing the reaction steps, it will attain equilibrium and it cannot be irreversible. Work done is maximum, work done not maximum, that is minimum. These are the differences between reversible and irreversible process. Still we have to discuss about entropy, enthalpy, work done, internal energy in the thermodynamics. So in the next class, we will see types of work, heat, internal energy. I hope you have understood whatever the thermodynamical variables and the functions or the processes we have discussed today. We'll meet in the next session. Thank you.